Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 4.1 entitled Exponential Functions. And today we're going to talk about what exponential functions are and how we can graph them. And then we're also going to apply exponential functions in compound interest. Now this whole chapter is going to be talking about exponential functions and different things that we can do with exponents. And we're going to start off with a really basic function, an exponential function. We're going to start off with f of x equals 2 to the x. And what makes an exponential function exponential is that the variable is always going to be in the exponent. So if we take a look at that function, 2 to the x, and we make a table of values to graph it, you're going to see what happens when you graph an exponential function and how it's different from a parabolic function or a polynomial function. Okay, so if we start plugging some values into this function, we'll have 2 to some power here. So if we have 2 to the negative 2, that's going to be 0.25. 2 to the negative 1 is going to be 0.5 or 1/2. Anything to a power of 0 is 1. And then we have 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. We got 16. And then 32. 64. Then we're going to skip all the way to 2 to the 10th, and that's going to be 1024. So if we go to graph this, you're going to see this shape take form really, really quickly. Okay, at -2, we've got 1/4. -1, we've got 1/2. At 0, we have 1. And then at 1, we have 2. 2, we have 4. 3, we have 6, 7, 8. So you can see that this graph is going to make a really sharp curve really early on. And hopefully you also notice that it's going to approach y equals 0 as a horizontal asymptote, but it's not going to touch it. Even if you plug in 2 to the negative 10, you're going to get a decimal. You're not going to get a number that's negative or below 0. So it's always going to be right above 0, but never going below y equals 0. Okay, so these functions are known to graph really, really quickly. And if we compared that to a parabolic function or a polynomial function, if we compared it to x squared, it would take a really long time for that x squared function to get into a value that's even close to what we had in just 10 values. When we did 2 to the 10th, we were already at 1,000. Here it would take us 30 squared to get to 900, and that's still not even 1,000. So an exponential function grows very dramatically. Here it says it has a dramatic change in the value of the function. Okay. And this is just a note about exponential functions. We want to remember that the base, the a, has to be greater than 0, and it can't be equal to 1, because if you have 1 to some power, you just get 1 out, and that's a constant function, so that doesn't really apply here for exponential functions. But you're going to have numbers that could be decimals, or they could be whole numbers. And if it's a decimal or if it's a whole number, that depends on whether or not it's exponential growth or exponential decay. Okay. And here's a reminder just that the larger in size number is going to be the base. The littler number, or in this case the variable, that's going to be your exponent. So that's just a reminder of those terms. And in your homework, you're going to have some simple problems to start you off that just want you to refresh your memory on how to evaluate exponential functions. So we're going to just plug in 2 here. So we would have 3 squared, which would be 9. Here they want to substitute in -2/3. So you would have 3 to the -2/3. And you can do that on your calculator. Oops, that's supposed to be a 2. Okay. And there you'll get a decimal, 0.48. You can take a number to a variable that represents a irrational number. So if we did 3 to pi, we would have 31.54. And you can take some base and raise it to a rational number as well, 4.73, or an irrational number. Okay, so basically you can put anything into that exponent is what they're trying to show you here. And lucky for us that our calculators have the ability to do this. On your calculator, when you're dealing with exponents, there's some exponents already programmed into the math menu. And you also have the little upside down V that's called the caret key on your calculator. So that's what you can use for your exponents. I'm sure you know that by now. Okay. Now, when we're doing our exponential functions, basically we just make a table of values and we plot all of our points. And we're going to graph these two. We're going to graph 3 to the x and then 1/3 to the x. And then we're going to compare them and we're going to discuss some of the graph's characteristics. So if we have x and f of x here, I'm going to make a table of values. So you're going to go to your calculator and put in y equals 3 to the x, and then go to your table of values. You want some negative values and some positive values. So let's just go from -3 to 3. And that's just a good rule when you're dealing with exponential functions, to take some negatives and some positive values. I'm going to start down here at 3. 3 to the third is 27. 3 squared is 9. 3 to the first is 3. Anything to power 0 is 1. And then remember, when you have a base and you're raising it to a negative power, you basically get the inverse of what the positive power was. So if 3 to the first is 3, 3 to the negative 1 is going to be 1/3. If 3 squared was 9, 3 to the negative second is going to be 1/9. If 3 to the third was 27, then 3 to the negative third will be 1/27. So again, you can write it like a fraction like that, or you can write it as a decimal. Decimals are probably easier to graph, but I just wanted you to see that pattern in the table of values. Okay, so at -3, that's really small. -2, also really small. -1 is 1/3. 0 is 1. 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this is what this function looks like. Again, it looks similar to the first one that we drew. It's going to go through 0, 1. It's going to have a horizontal asymptote of y equals 0. And it grows really, really fast. I can't even put 327 on there. Okay. For our other function here, for our g of x function, when we're in class, I'll ask you to do the same values in your table. And I'll ask, what do you think is going to happen with our values? And hopefully you'll see that 3 and 1/3 are reciprocals. So that's basically going to flip-flop our table of values. So if we have 1/3 to the -3, that's going to be 27. 1/3 to the -2, that's going to be 9. Then we'll have 3 and 1. Then we get 1/3 and 1/9 and 1/27. Okay, so when we graph this function, if we're in class, I'm going to ask you, what do you think is going to happen when we graph it? And you should notice that it's going to be the opposites of what we did before. 3, there's 1, we have a third, and we have a ninth. So this graph is going to decrease really, really fast. Okay, so in our first graph, when that was graphed and it went up really, really fast, that's an increase, so that's growth. That's exponential growth. This graph in part B, where it's decreasing really, really fast, that's called exponential decay. And the way that you can look at a function and tell if it's growth or decay is to look at the base. If your base is a whole number, you've got growth. If your base is some sort of fraction or decimal between 0 and 1, then it's going to be decay. So basically, if your base is greater than 1, it's going to be growth. If your base is between 0 and 1, then it's going to be decay. Notice again, for the decay graph, we approach y equals 0, but we never actually touch it. And again, this graph goes through 0, 1. So did part A, went through 0, 1. So all of the exponential growth and decay graphs are always going to go through 0, 1 because anything to a power of 0 is 1. The domain for both of these is going to be all real numbers. The range for both of these is going to be everything greater than y equals 0, or all the y is greater than 0. And you can have growth and decay functions that are in the third and the fourth quadrants. You can put a negative out front of the whole function and flip-flop them around the x-axis, or reflect them around the x-axis. Okay, but most of the time our range is going to be everything greater than 0. And again, remember that that horizontal asymptote is always going to be y equals 0. So those are just a few characteristics that are always going to apply to all of our exponential graphs. Okay, and this is just a characteristic that we noticed when we were making our table of values about how when you take a function and you raise it to a negative exponential value, when you take a base and you raise it to a negative exponent, then you're going to get the same thing as basically 1 over that base to a positive exponent. So we noticed that when we were making our table of values. Oops. And the book does a nice job with showing these pictures of families of exponential functions. So here we have, y to the, or y equals 1/2 to the x, 1/3 to the x, 1/5, 1/10, and then you've got 10 to the x, 5 to the x, 3 to the x, 2 to the x. So these are families. And notice that they all go through the same point. They all go through 0, 1. And the families are color-coded here. So you can see that growth would be 2 to the x, and the decay would be 1/2 to the x. Okay. Okay, we've already talked about how all the graphs go through 0, 1. And this we talked about as well, how if your base is between 0 and 1, you're going to have exponential decay. And if your base is greater than 1, then you're going to have exponential growth. Okay, they call them decreasing and increasing rapidly, but it's still decay and growth. And then we talked about how the x-axis is going to be your horizontal asymptote. Okay, how that horizontal asymptote is always going to be y equals 0. We talked about that. Okay, and here you can see again in this picture with the family of the exponential functions, they're all approaching the x-axis, but they never touch it. They never cross it. So these are all characteristics that we've already seen in example 2. And we talked about how our domain is going to be all real numbers, and our range is going to be everything greater than 0, or going from 0 to positive infinity. Okay, so all of those characteristics we've already seen. Now for example 3, this is kind of cool. This is how you can take a graph and find the function for that graph. Find the exponential function for that graph. So basically, we have some exponential function. It's going to be f of x equals a to the x. Okay, they want us to figure out what the a is. So they want us to figure out, is it 2 to the x? Is it 3 to the x? Is it 1/2 to the x? Or 1/3 to the x? Okay, and all we have for information is the picture of our graph, so we can tell if it's growth or decay, and then a ordered pair on the graph. Now this ordered pair tells us what you put into the function That's your x value. And then what you get out, which is your y value. So here, if I have f of x equals a to the x, that means I put 2 into the function for x, and I get 25 out for f of x. Okay? So if I was making my table of values, if I had x and f of x, 2 would be the value I'd put in, 25 is the value that I get out. So if I'm going to substitute those back into this original function here, I would have a to the second equals 25. Okay, the 25 is being substituted in for the f of x, and the 2 is being substituted in for the x. So you're basically trying to figure out what a is. So what squared is 25? Oh, that's got to be 5. So that means my original function was f of x equals 5 to the x. So that's pretty slick, pretty clever. It's just substitution. But you have to stop and think, okay, where do I substitute in each of the numbers? What do they mean? Okay. And this graph is increasing rapidly, so it's definitely a growth. So we want our base to be a whole number greater than 1. And for part B, I'm going to do the same thing. Okay. This graph is decreasing rapidly, so this is going to be exponential decay. So our answer should be a number between 0 and 1. Okay, here again, this is my x value of 3. So if you want to think of it like a little table of values, we have x and f of x. Okay, they put 3 into the function for x, and they got 1/8 out for y, or for f of x. So that means I'll have 1/8 equals a to the third power. Okay, now if you're solving this, you basically have to think, okay, what to the third power would get me 1/8? Or you could take a 1/8 in your calculator and take the cubed root of it. Okay, so if you're trying to solve for a and it's cubed, you want to undo that by doing the cubed root. So there's 2 ways to think of this one, since it's not as intuitive as what we did for part A. For part A, we know that 5 squared is 25, but you're really taking the square root of both sides there. You could think of it that way too. So here you have to think, okay, what to a power of 3 is going to be 1/8? Well, that's going to be 1/2. Because 2 times 2 is 4 times 2 is 8. So 2 to the third power is 8, and then it has to be a fraction, so it has to be 1/2. So that means my original function was 1/2 to the x. So you will see some problems like that in your homework as well. Okay, for example 5 now, we're going to compare these two functions, and it says to compare the rates of growth for the exponential functions. So if we make our table of values, I'm going to kind of make a combined table of values here. I'll have my f of x function, and then I'm also going to have my g of x function. And I'm going to go from -2 to 5, okay? Because that's going to give us a good picture. Again, when you're doing exponential functions and their table of values, you want to make sure you have some negatives and some positives. So my f of x function is 2 to the x. That's basically what we did earlier. Okay, so we have those values written down on a previous slide or a previous part of your notes. And if you didn't remember that they were written down, we can just regenerate them here. And then we also have x squared. So this is our parabola function. So we're comparing an exponential to a parabolic function here. And we've already talked about how exponential functions grow much faster than parabolic functions. Okay. Now notice there's a couple of values here that are going to be the same. 2, 4 is the same for both of them, and 4, 16 is also the same. Okay. So if I graph this function, let me see here. On my axes. Okay, so I have -2 and then a fourth negative 1.5, 0, 1. All exponential functions have to go through 0, 1. 1, 2, 2, 4, 3, 5, 6, 7, 8. Okay, so there's my exponential function. And then my parabolic function, let's see, negative 2, 1, 2, 3, 4, negative 1, 1, 0, 0, and 1, 1, and 2, 4, so it's going to go through that same point. And it also has 3, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so just the way I've drawn it a little off here because the parabola is really going to stay a little bit wider than the other function. Okay, and then it says to compare the rates of growth. Well, obviously you can tell that the exponential function is going to grow much faster. And what the book does a good job of is that it really zooms in on a couple of the values. Okay, at 2, I guess this would be 2, 4. Okay, you can see that they're the same. So that's at the ordered pair 2, 4. And here we have 2, 4, and then we also have the 4, 16. Okay, so again, those ordered pairs are going to be the same for both graphs. But if you look between them, okay, the blue function is our parabolic function. So you can see that it starts off low, and then it gets a little bit ahead of the exponential function, but then it tapers off again. So that exponential function starts high, and then it goes a little low, and then all of a sudden it jumps ahead, and it starts to grow really, really fast. And if you zoom way out, you can see that at the beginning, the functions are very close, which is what I was drawing on the previous slide. But if we kept going and enlarged our viewing rectangle, you can see that the exponential function really grows much faster, and this parabolic function is going to be really wide compared to the exponential function that's going to be very steep and narrow. So those are the observations that you want to make. And again, we've talked about that earlier when we did our first couple of examples. Now, the best application, or one of the best applications for exponents, is compound interest and simple interest. Okay? So when you're dealing with interest, you have an amount of money that you're putting into some sort of investment, and they call that your principal. So that's going to be P. And A is going to be the amount of money that you get out. Okay? And you're going to invest that invest that money, that principal, at a certain interest rate. So that interest rate they call I. Sometimes they call it R, depending on the type of equation that you're looking at. There's all kinds of different equations for compound interest, but this one we're just going to call it I for that interest rate. Okay? And then you have a certain amount of time. You have a certain time period. So it could be days, it could be months, weeks, years, whatever. Okay? So your basic function is this part right here. A equals P plus P times I. So they take the principal, and then they take the interest rate on that principal for the certain amount of time. So if you're dealing with a certain percent, you know you have to take that percent and multiply it by that original number. Okay? And then you add those two together. So that's your new amount. And how they rewrote that was they took P out as a GCF. So you have your principal times 1 plus whatever your interest rate is. Okay? Now, if you have this interest rate compounded, which means you just let your money sit in this account for month after month, year after year, this interest rate will be applied a certain amount of times. Now, it could be compounded one time, like it is written up here, or it could be compounded twice, maybe 2 times a year. Okay, so when that happens, then they're going to square your 1 plus your interest rate. and then multiply that by your principal. Okay? And if it's compounded 3 times, then you cube it. If it's compounded 4 times, you'd fourth it, etc., etc., etc. So instead of just having a number there, we put a variable. We put k, and that's the number of periods, or the amount of time that that gets compounded, or the number of times that that gets compounded. So there's one other thing that they're going to do to this equation to tweak it a little bit and get our final equation that we're going to use. And that deals with our interest. Okay? It says down here if the annual interest rate is R, and if the interest is compounded n times per year, then each time period the interest rate is R divided by n. So you get that whole rate all together for your one period, but they're only going to do it a certain number of times. So to get our final formula now, they're going to take that I and they're going to replace it with an R divided by n. So this is the formula that we're going to use for our compound interest. So P is your principal. The A of T, that's the amount that you get out after so many years. The 1 is just going to stay a 1. Your R is your rate. The N is the number of times that you're being compounded. And then you still have it to the N times T. So they did modify that T in the previous version a little bit because they're multiplying it by the N. And that just means that it's the number of times that they compound it times the number of years that they've done that. Okay? So this box is a really good box to look at in your book because it explains the formula and everything that the formula is, which is helpful when you're applying it in a problem like this. So we have example 6 and example 7, and then we're done. So here you have a sum of $1,000, and you're going to invest it at an interest rate of 12% per year. Now remember, when we're dealing with percents in these types of problems, we're going to have to convert them to decimals when we substitute them into the equation. So it says find the amounts in the account after 3 years. So that will be our time. If the interest rate is compounded annually, semi-annually, quarterly, monthly, and then daily. So we've got 1, 2, 3, 4, 5 amounts that we're going to have to do. Now, we're going to do just one, so you see how to substitute things in. On the next slide, they have a chart that shows every substitution and every value that you get out. Okay? So on your homework, you might have to do a problem like this, and you really might have to go through and do every single one of these, all 5 substitutions, and get 5 answers. But if we start with our equation, we'll have P times 1 plus R over N times, or I'm sorry, to the N times T. Okay, that's our interest equation, our compounded interest. And the amount is what we're going to be finding. It says find the amount. So A is what I'm finding. The $1,000, that's my principal. That's what I put in. A 1's going to stay a 1. Now my rate was 12%, so I'm going to make it 0.12. Move the decimal back 2 places to the left. Now the first amount they want me to find is annually. So that means it's 1 time, 1 year. Okay. And then my time is going to be 3 years. And I'm doing that 1 time each year. Okay. And I'll show you the answer in a moment because it's in the table on the other slide. But this is just a calculator problem now. When you plug this into your calculator, you want to do the 0.12 and divide it by, in this case, 1. So that doesn't change it. And then add the 1 to it. Okay, so you'll have the 1,000 and then the 1.12 to the 3. Now remember your order of operations. There are so many times when students mess this up, and it's just because of simple order of operation errors. You have to do the 1.12 to the 3rd power, get an answer, and then multiply it by the 1,000. Okay, so that would be our annual amount. If we want to do another substitution, if we wanted to do the semi-annual, 1 plus the 0.12, and we would divide it by 2 because it's 2 times a year, and then we would have the 3 times 2. Okay? So again, you'd have to do the 0.12 divided by 2, add that to the 1, get an answer, raise it to the 6th power, get an answer, and then multiply it by the 1,000. But the nice thing is that they have this all worked out here. Okay? So annually means once, semi-annually is twice, quarterly is 4, just like there's 4 quarters in a dollar. Monthly, there's 12 months in a year. Daily, 365. So if you're ever confused on the amount of time that they're asking for on a quiz or a test question, ask and I can clarify that. Okay? Because I'm not testing you on knowing that knowledge so much as I am the application of the equation to get your answer. Okay? So basically, after a year, you'd have $1,404.93. Okay? If it's compounded semi-annually, you get a little bit more. You get $1,418. Okay? So notice that even if it's compounded daily, you're really only getting, what, about 29 more dollars in that situation? Okay? So there's not a whole lot of difference in the amounts. Okay? But you can see how compounding it more does get you a little bit more interest or a little bit more money out. Okay, now aside from compound interest, there's also simple interest. Okay, and the annual percentage yield is what they're referring to as the simple interest. Okay, so that's the rate that yields the same amount at the end of 1 year. Okay, so your book, when they're talking about using simple interest, they'll refer to it as the annual percentage yield. So if you see that in your homework, this is what they're going to be referring to. Okay, so we're still going to use that same formula that we've been using. The formula is not changing. It's just the way that it's written. Here it's going to say that it's compounded daily. Okay, so we're going to find the annual percentage yield for an investment that earns a rate of 6% per year. Okay, so find the annual percentage year. Okay, if we go to our equation, okay, they don't tell us how much we're putting in. Okay, we are going to start with the 1, and then with 6%, so that's 0.06. Now, if it's compounded daily, we're going to put the 365 there. And then the 365 will be times 1 because it's per year. Okay, so we're doing this 1 time a year. Okay, now if it says find the annual percentage yield, now the one thing that we're kind of missing here, I mean, they don't tell us the principal amount. They don't tell us that. But it says if an investment earns a compounded interest, then the annual percentage yield is the simple interest rate. It's the rate that yields the same amount at the end of 1 year. Okay, so this is sometimes where students get confused because they think, oh, I don't have a value for P, I don't have a value for A, what am I really finding? So when it says find the annual percentage yield, that really means you're finding the rate. Okay, so basically we just have to focus in on this part right there. Okay, so if we take the 0.06 and divide it by the 365 and add 1 to it, we'll end up with 1.06183 to the 365. Okay, so if we start simplifying this equation, this is what we get. But this part right here, that's my rate. Okay, now remember, back a few slides, when we were doing this, we had the 1 plus a bunch of stuff, and this bunch of stuff right here, Okay, that's really the rate. This 1 is just a 1 that stays in the equation. Okay, so this part here is really a 1 plus my rate, whatever it is. Okay, so it's really the 0.06183. That's my rate. So here is my rate written as a decimal. Now all I have to do is move the decimal over. So 6.183% is going to be my rate, or the annual percentage yield. So that's the rate that I would have to invest my money at to get the same amount after a year, okay? Or to get the same amount out after a year. So it's a little tricky, it's a little confusing. Okay, I don't know why they call it annual percentage yield. I don't know why they can't just call it rate. I don't know why the book can't just say find the rate, but that's what you need to do for those types of problems when they're talking about the annual percentage yield. So work on these problems, practice these concepts. Remember, make a table of values for your graphs. And when you're dealing with the compound interest stuff, make sure you're paying attention to order of operations when you're calculating those in your calculator. And if you have any questions, come on in and see me before school.